Hello and welcome. In this brief video, we're going to look at some vector properties. So we've heard about vector magnitude and vector direction. We're going to add a little bit of operational content to that. So first of all, we use the word magnitude typically to describe length, but length is not a very good word because what does length mean in 4 or 5 dimensions? We will be looking at vectors that are n-dimensional, and what that basically means is that we're not going to limit ourselves to vectors that say only have 2 components, but that have a component here, and perhaps there are n of those components. And so how do you represent an n-dimensional vector? Well, we can only go as high as 3 dimensions, and we can represent some sort of vector in here and that has some sort of height. And we can measure that length. We can definitely put a ruler to it if we could physically handle that vector. But when you're in n dimensions, well, you can have an x, a y, or an x1, an x2, and an x3 axis. So we'll use the word magnitude instead of the word length, just because it's more broad. Now, even when you compute the magnitude of larger vectors, it does tell you something about the size of its components, but it really doesn't characterize length in the physical sense anymore. So suppose we want to find the magnitude of this vector here, 3, 4. That means we have a vector that is located 3 units in the x direction, and that's located 4 units in the y direction. So what we often like to do is we like to work with right triangles. And in this particular scenario, if we look at the x component as being one side or one leg of that right triangle, and we look at the y component as being the other side of that right triangle. And yes, we can argue that this is a right angle here because this length here runs parallel to the y-axis, this runs parallel to the x-axis, and the x and y-axes are perpendicular. So if I want to know the magnitude of a vector, which by the way, if x is the vector 3, 4, then to denote the magnitude, we can't just say x is some number. We have to denote that it's the length of that vector. So we put this absolute value sign around it. And absolute value, by the way, does mean how big is something. So if this is 3 and this is 4, we know from Pythagorean Theorem that if this is vector x here, the length of vector x squared is going to equal 3 squared plus 4 squared. And so to find the length of x, this notation just means the length of x. You never remove these brackets. So when we take the square root of both sides, we are going to get the square root of 3 squared plus 4 squared, which gives us the square root of 25, which is 5. So this length of this hypotenuse here is 5 units long. And so we can say, in short, the length of x is 5, or whatever kind of units we want to measure that in. Now the direction of a vector is typically measured as an angle, and this angle is going to be relative to the positive x-axis. That's usually how we measure angles. Now, in dealing with nautical measurements or dealing with aerial measurements, we may use bearing coordinates where it's so many degrees north of south, but to keep the mathematics somewhat simple, we will describe it as the angle relative to the positive x-axis. So once again, if we form our right triangle here, and we already know those side lengths are 3 and 4, we just need to find a trigonometric relationship that relates right triangle sides, and we know that the tangent of theta is going to be the opposite side, which is 4, divided by the side adjacent to theta, not the hypotenuse, but the side, which is 3. And so then theta is going to be the arctangent, or the inverse tangent of 4 over 3. Remember, the tangent of an angle tells us the ratio of rise to run, but the inverse tangent says what angle has a rise to run ratio of 4 to 3. So it's just important that you select your mode carefully, making sure that you're in degrees if you want to be in degrees. And because it makes sense to reference angles as degrees, if they're physical angles, then we can say that this is about 53 degrees if we were to round to the nearest degree. So again, using basically right triangle geometry, we can find side lengths, we can find the length of a vector, we can find the angle of the vector, and so on and so forth. Now, when we're working in higher dimensions in R3, we have to reestablish our measure of magnitude because now we're dealing with a three-dimensional vector. So, by the way, we often don't deal with direction of a vector in R3, and the reason is that it's hard to reference an angle. So, or hard to reference, talk about an angle relative to where. So if this is an angle somewhere, or a vector somewhere in here, and that's its corresponding height, then what angle are you measuring? Well, are you measuring this angle, that's the angle between the vector and the xy plane? Or are you going to measure this vector, which is this angle, which is the angle between the vector and the x-axis? Or are you going to measure this angle over here, which is relative to the y-axis? Or do you even want to measure the vertical angle relative to the z-axis? So there's lots of choices, and therefore, and if we don't have to, we're not going to worry about that angle in 3 dimensions. Now, magnitude can be found by multiple iterations of Pythagorean theorem. Rather than to just state the formula, which might look familiar, we can use Pythagorean theorem. So let's say we have this vector 3, 2, 4, which the tip of this vector right here is located 3 units in the x direction. So there's our 3 units, 2 units in the y direction, that's this way, and then 4 units above the xy plane, which is this length here. So that's 4, this length is 3, this length is 2. Now what we want is we want to know what's the length of this vector w. So to find the length of the vector, well, first of all, here's a right triangle right here between this vector, or this line segment here, h, and this line segment here, g. But the problem is, although we know the length of g, we don't know the length of h. So we kind of have to tinker around down here in this xy plane to find it. And again, the reason we know that this is a right angle is because the z component is perpendicular. That's the distance directly above the xy plane. So this is perpendicular to the xy plane, and h lies inside of that xy plane. So here we see we also have a right triangle right there, this triangle here, and the reason we know that's right is because 3 is the length along the x-axis, 2 is parallel to the y-axis, and x and y-axes are perpendicular. So we can first of all resolve the length of h. Let's just call that h vector. And the square of h, of the length of h, is going to be 3 squared plus 2 squared. But then when we square root both sides to find the hypotenuse, we get this expression here. Now we can equate that or approximate that, but let's leave it alone for a second. Now to relate w, so if we know that the length of h is whatever this expression here evaluates to be, we also know that the length of h squared plus 4 squared, that's the length of that leg right there, is going to equal the magnitude of w squared. So to get the length of w, I just have to take the square root of both sides. Take that away right there. We'll take the square root of this side here. Now that's going to be the length of w. Now I'm going to go ahead and plug in what I know to be the length of h. So this is going to be the square root of the magnitude of h squared, which is the square root of 3 squared plus 2 squared. So that's just me substituting this component in. But that's going to get squared plus the square of 4. And if you look at what happens here, the square root squared will just unlock what's under the radical, 3 squared plus 2 squared plus 4 squared. And the reason we didn't evaluate this expression is to really clearly see that if we have a vector that contains 3 components, then the length of that vector is simply going to be the square root of the components of that vector squared. So to generalize this, even though we just described that we can't talk about length in n dimensions, so n dimensions could be 100 dimensions, there could be 100 values in here. The meaning of those 100 values could be you collect 100 pieces of information on each individual, so it could be their height, their weight, their arm length, etc. But to compute the magnitude of that vector, which we'll see later on has many applications and uses, all we have to do is take the square root of the sum of all of the components squared. So x1 squared plus x2 squared all the way down to xn squared. And that gives us those components there. So even though it doesn't tell us length, if you imagine that these numbers are really big in magnitude, they're going to get squared, and they're all going to get added together and square rooted. So the bigger each of these components are, the bigger that magnitude will be as well. Now, one of the other things we like to do with vectors, I'll just mention this off to the side here, is the unit vector. And the unit vector is a vector of length 1. So if we want to take a vector like, say, 3, 4, and we want to find the vector that points in that same direction, over 3, up 4, so there's the vector 3, 4, but what I want to do is kind of concatenate it, make it a lot shorter so that its length is exactly 1 unit long. How might we do that? Well, let's think about an analogy. If I were to go out and buy a board at my local lumber store, and this board is 8 feet long, and I want to chop it up so that I have 1 foot segments. Well, in order to do that, we have to break 8 feet up into 8 pieces. So it'll look roughly like this. And so then I have piece 1, 2, all the way up to piece 8 right there. So we have to take 8 feet and divide it into 8 pieces. And so that comes out to 1 foot per 1 piece. So that gives me 1 segment that is 1 foot long. So the same kind of analogy applies to vectors. If you take a vector, x, and you divide it by its magnitude, what does it mean to divide a vector by its magnitude? Well, that's the same thing as saying taking 1 over the length of that vector and multiplying it as a scalar. This here is going to be some scalar, multiplying that by the components of the vector itself. So let's see how this works. So in our case, 3, 4, so for the vector 3, 4, we already know that its length, if that's vector x, we know that its length is 5, we found that. And so if I take x and I multiply it by 1 over its length, that's going to be 1/5 of the vector 3, 4. And when we scale a vector, we know that that's going to be 1/5 times 3, which is 3/5, and 1/5 times 4, which is 4/5. And this right here is a unit vector that points in exactly the same direction as the original vector. So this guy here is going to be the vector 3/5, 4/5, and he is exactly 1 unit long. And how do we just verify that as a check? We can compute the length of the vector containing components 3/5 and 4/5. And to do that, of course, it's going to be the square root of the components squared, added together. And so when we square 3/5, we get 9/25. When we square 4/5, we get 16/25. And when we take the square root of that, well, 9 plus 16 is 25. You can see where this is going. We get the square root of 25/25, which is the square root of 1, which comes out exactly to 1. And that's our check, our verification. So these are 3 important features: magnitude, direction, and the unit vector. These are 3 things that we'll use very commonly.